Okay, this is section 1.5. This is using graphs and tables of functions. Here is your journal choice. If you want to copy this down, I think it's a pretty easy one, so have fun writing about it. Here we go. Objective and what's the point? In this section, we are going to discuss how graphs can tell stories and how to use technology to create lists of function values. The technology part, we should have already gone over in class by the time you watch this video. It's about creating a table on your graphing calculator. Why are we going to do this? Well, this section has many applications. This is all about understanding what a graph or table is telling us. We are going to tell the story of a graph. Every field imaginable comes across tables and graphs, and we need to be able to decipher what those tables and graphs are telling us. Not only that, but the science portion of the ACT a lot of times is about deciphering graphs, so this is going to help you beyond math in the academic setting as well. Okay, I'm sorry, that's really funny. His name is Frankfurter. Frankfurter rode his bicycle to Chuck Rowe's house to plan a back-to-school picnic. The boys then rode a short distance to the park and then back to Frank's house. The graph below models Frank's trip, where T is time in minutes and D is Frank's distance from home in miles. Okay, the next two slides I'm going to show you is everything written down, what I'm getting ready to explain to you now. So if you want to wait and then pause the video on the next slide and write some of that stuff down, you can. Otherwise, you can just listen and take notes off this or look in your book on page 33 and follow along. Here's how it works. Time here is on the x-axis because that's what the independent variable is. That is what we are choosing to look at his trip in respect to. They're measuring the miles and distance from home, and that is your dependent variable because the distance will depend on the time in this trip. Okay, so at this point, he just started. He's in his house. Maybe he's taking a nap. Maybe he is packing the lunchbox. Who knows? Okay, but at this point, he's at home. When I tell a story, I get a little creative. So we get here. This is the next significant value. When I say significant values, that's when there's going to be a change in the graph. That's your best way of telling a story, is to look at these values. This is telling me what? Well, it looks like he's been going here for, drop this down, looks like 45 minutes. And in that 45-minute time, he has rode his bicycle, 6 miles? So what does this tell me in terms of the story? Well, he rode his bicycle to Chuck Rowe's house, and then it looks like here something happens. The time is going on, obviously, but the distance is saying. I'm guessing that Chuck Rowe must live how far away from Frank? Looks like 6 miles. He rode his bike to Chuck's house, and it was 6 miles away. It took him 45 minutes. Now, this line is straight. That also tells me something significant. That means he's going at a constant pace because that rate of change that you talked about in Algebra 1B is constant. I could even ask you what speed he was going on. You could figure that out by dividing out the miles per hour if you wanted to. But we definitely see him. He's going at a constant speed, 45 minutes, 6 miles to Chuck's house. What happened when he picked him up? He rang the doorbell. Chuck was like, oh my gosh, I don't have my shoes on. I'm sorry. So he puts his shoes on. And this pause here, where no distance is being gained, he was getting ready, getting his, I guess, picnic basket. I don't have a picnic basket, but I think Chuck does. So he's getting his picnic basket together and getting ready for his picnic. Okay? Then, this is 1 hour into the trip. Then they are going on the road again. How do I know they're on the road again? Because distance is changing from Frank's house. So he's from here to here. This is the next significant point. So this is 30 minutes now. What's he doing in those 30 minutes? Well, they are this time going, it was from 6 miles to 12. They're going an additional 6 miles. So what does this tell me? Well, I'm thinking Chuck must live 6 miles from the park, or wherever they're going. Yes, the park. This line segment here is a little bit steeper than this line segment. That's telling me that they were A, either hungry, or B, excited, or maybe Frank is a little lazy. Maybe Frank could have pushed himself a little bit more here. But they're definitely going at a quicker speed because that rate of change is steeper, meaning they're going faster. Okay, next significant point is right here. We are at from 90 to 120 minutes. That looks like they took, what, 30 minutes for lunch. They're at the park here. They're not going any further from his house. The distance is staying the same. 30 minutes, they're stopping and eating. Okay, after that point, we are going here. Now, notice this time there's no time stoppage. This time is continuous. Whenever Frank and Chuck rode together, this is probably the same location as here, so we're going back to Chuck's house. They're going faster again. Again, it's either because they ride faster together or maybe Chuck had to go to the bathroom or something. They're going a little faster. This time, Frank does not stop. He merely drops off Chuck. I know this because there's no stoppage in time. However, again, when Frank is going back to his house, notice this is a little flatter segment. The rate of change is a little less, which means that lazy Frank, maybe the food is settling in. He's like, oh, I shouldn't have eaten that last hamburger or whatever. I guess they don't take a hamburger to the picnic. Sub sandwich. I don't know what you bring to a picnic. But he went a little slower here. Okay, that's my story from the graph. I went on 3 minutes about it. I don't think you'll go 3 minutes on a homework question, but I just want you to really see all the things you can imply from graphs. Okay, here is a little bit more broke down. If you want to write any of this down, pause the video. Feel free to do so. These are things we already talked about. Here's more all the way to the end. Going back home. Nice trip. Okay, now the rest of this flip chart, we're just going to go over some examples from yesterday and some notation things. Some of this will show up on your test and quiz coming up, so please pay attention to this. These are some example problems. Okay, determine whether y is a function of x. This is review. Does y depend on x, which means that x would be the independent. That is what you check. You check the x. What am I checking for? We're checking for repeats. Independent. Okay, so I'm checking the x for repeats. 3, 4, 5, 6, 7. No repeats. So is it a function? Absolutely yes. Okay, determine whether y is a function of x. Again, we're checking the x's here. Any repeats? -6, -5. Okay, we got -5 is a repeat and 0 is a repeat. I think that's it. Okay. Checking the -5s, they have different values of y, so that would be a no. Notice the zeros have matching ones. That would have been okay if just the zeros were there, but because the -5s have different values of y that correspond with them, that is not a function. Okay, domain and range. Please, please, please listen to this. The notation, you do not have to do set builder notation here when you have a table. I'm going to write this down because you're going to miss this later. When you have a table, list the domain. Okay? You can just write D for domain if you want to. Still do the forehead, nose, and chin, but you don't have to do the set of all x thing. What is my domain in this case? I don't know that it's continuous. I don't know that it goes from 3.1 to 8.4. Maybe there are some things that you could not possibly have as an answer. There's no context to this problem. So when I do my domain, I'm going to list. I'm going to just list them out. You could put them in the order that they came if you want. I think it's mathematically polite to put them in numerical order. Some of you might not care that much, and that's okay too. Just make sure that you do not put a inequality here, because we don't know that this is continuous. That's the domain. That is what x can be. What can the range be? This one's easy. What's the range going to be? 0. That's all that I'm given for this table. When you have a table, list it. Don't make it harder than it is. Okay. Moving on. Still finding domain, finding the range, determining the argument or value that they ask for. Okay? Table, what I just tell you, if it's a table, you need to list it. So the domain, I'm not going to put a D this time because the domain has told me to be A. Again, you don't have to put it in order if you don't want to, so this time I'm just going to write it down. What can x be? That's domain. This time there's no x, so this time we're talking about v actually. This time d of v for range, I would just put the same. How do I know it's the same? Because look, They all match up. Okay, this is important. What is this asking me? D of negative 4. That's the same thing as saying D of V. What is replaced here? The V is replaced here, so they're asking what is the value of the function when V is negative 4? When V is negative 4, what is the value of the function? Negative 4. Okay, on graphs, this is where you will do your set builder notation with inequalities if necessary. Okay, the domain. What is the domain here? What can x be? Well, let's look. This is a line. X is left to right on the graph. Can I go forever in the left and right direction? Well, I am picking 0. They picked 1. We're going forever to the positive values of x. I know it's forever because there are a line here. This little arrow is telling me go forever in the upper left here also. So I could pick any positive number I want and it would be on this line. I could pick any negative number I want and it would be on this line. Left to right is continuous. The domain here is all real numbers. You could put set of all x such that x, we say, is an element of the real numbers. This is a math symbol you will use in the future. It means is an element of. Okay? This double R means the real number system. It's a shortcut way of writing things. You'll have to use that a lot. B, what is the range? What can y be? This is going up and down now because y is up and down. What values will I get? I'm going to get all sorts of positive values up here, all sorts of negative values down here. There's no stoppage in the line. Anything is for grabs. So again, this is all real numbers. Set of all y such that y is an element of the real numbers. And this time they're asking if y of x equals 4. Y of x is the name of this function. They're saying the whole value y equals 4. So where does y equal 4? Well, here's where y equals 4. Take it over to your graph, which is right here. What is the x value that coincides with that? Negative 4. So when x is negative 4, y of x is 4. Okay, I really like this one. This one's a little trickier. Domain and range. This is going to be a little hard for you guys at first. You're going to get better at this. We're going to practice this all year. What can x be in this graph? Remember, x is left to right on the graph because you're talking about your x-axis. What values can I pick for x? Notice, this graph is really staying here in quadrant 2, which means I cannot pick a positive value to plug in. If I plug in 5, my graph will never be here. Okay? I like to think of it, can I draw a boundary line somewhere and like fence in the graph? Yeah, I could. Oops. I could draw it right here and I will never touch that graph. This is going to be set of all x such that I need numbers for x that are less than 0. I don't believe it will ever touch 0. It looks like it's getting really, really close to 0, but it will never touch it. So the only thing I can plug into this function will be negative numbers. Okay? How about y? Set of all y such that. Again, this is now looking up and down. The y-axis is up and down. So where is there a boundary line? Same type of thing here. But this time I'm not talking about negative values for y, I'm talking about positive values for y. So in this case, y will be greater than 0. Those are my boundary lines, so that's what my region needs to tell me. X has to be less than 0, that would be this side of the graph, right here. And y is greater than 0, that would be this part of the graph. So where do they overlap? Right here. If you're a little confused by that, we can talk more about it tomorrow, and you'll have some examples to look at. It will get easier, I promise you that. Okay, here we go with g of negative 1. That's the same thing as saying g of x. So we're looking where is x equal negative 1? X is negative 1 right here. Take it up to the graph, and we are at, looks like 1. I don't know if it's quite 1, but that's what it looks like. Okay, if you have any questions, mark them down. Let's talk about it tomorrow. How about this one? In 7 and 8, the typical growth pattern of a dog over a 2-year period is shown in this graph. W of A gives the percent of the adult dog's weight when the dog is A months old. Okay? So what it looks like it happens here, and I knew this, puppies grow quick and then they kind of level off because I think dogs get older quicker or something like that. Okay, domain and range of this function. This function is limited because we are only talking about 2 years. Okay, so the domain, what can I choose for x? This is a continuous line, so we're going to do the set builder notation, set of all x such that. What are my limits on x? Well, x here is age in months. Well, you can't have less than 0 months. So you got 0 less than or equal to x, and when are we stopping the months? 24. We are collecting data at the 24, so that's why we put the equal sign to include that in our domain. The range, what do I got for y? Set of all y such that. Up and down this time. This looks like 5. I don't believe that they're, I guess maybe they're saying before the dog comes out they're 5 pounds or percent, 5% of their weight when they come out. So I guess we are going to start at 5. Less than or equal to y. And we never quite get to 100, so maybe you say 99. I'd take a variety of answers here, but as long as I could tell you, look at the graph. Okay? Estimate W of 12. What does this mean in real life? Well, W of 12 is the same thing as W of A is our function. So where does A equal 12? We go here. That's where it is. Go on up. And it looks like maybe W of 12 is, I'm going to erase that. It's in my way. 88. I don't know if you disagree or not. W of 12 is 88. What does that mean? Well, this is month. So when a dog is 12 months old, be specific here. Then we're talking about percent of his adult dog's weight. He is at 88% of his adult weight. And that's what I have for this. Okay, this is domain and range in a nutshell. I'm sure you love math just like I do, and I will see you tomorrow. Thanks.